when a word doesn't mean what you think it means. So you might think simple means easy. It doesn't here. Okay. Physics, materials. Wait, are you sure? Kinetic theory, yeah, okay. Do you mind opening one of the windows, please? You're going to be okay with that, aren't you? Of course you are. You're tough. Right, so you can write this down. Oh, you have to go all the way around. I thought you could I don't mind if you stand on the table. It won't offend me. Okay, did you write this down? Yeah. There we go. I think we're all getting too hot, right? I know I am, anyways. Continue. You got this title? Yeah. Quite a bit to do. Now, just to start with, have we talked about pressure? We have. Do you remember the definition of pressure?
Pressure.
Yeah.
Mass over.
Oh no, not this one. That's density.
Pressure.
Force over area. Yeah. It basically means how much something is pushing on something else. So you don't need to write this. And you remember the formula is F over A, and P is the pressure, F is the force, and A is the area. And the units, of course, are pascals. And we say 1 pascal of pressure is when 1 newton of force pushes at right angles on 1 meter squared, the same as 1 newton per meter squared. I think you have all this information already, don't you? Did I give this to you in a previous lesson? I feel like I have. The lesson on work, maybe. Right? Yeah, so I can continue from here because you have this already.
Yeah.
Yeah, you do. Yeah. Good. Now, this is just a reminder of the formula for pressure, which we'll need coming up. So we'll consider our ideal gas. What does the word ideal mean in English? Perfect might be too strong, and suitable might be too weak. Good.
We won.
Ideal, most suitable. Yeah, actually that's pretty close. Ideal meaning what we would like. So for an ideal gas, it's a gas that we would like, meaning a gas that has properties that we desire, that we like. So what is an ideal gas? We shall assume some things about the gas. So number 1, for our gas to be ideal, to behave the way we would like, we would want the gas to have a low density because it makes the calculations, the formula makes more sense when the density is low, the formula I'm about to do. I mean, the gas could be a high density, but then it's becoming more like a solid. So when we think about a gas, we think about it being a low density. So our first assumption is a low density. Oh, I should say, in the exam, a normal exam question for this would be, what are the assumptions of an ideal gas, or what are the properties of an ideal gas? So the first property you'll need to know is that we consider the ideal gas to be low density. So this is property 1. Got that? Yeah. Okay. Low density of what? So we consider it to be a low density of colliding particles. So lots of little particles moving around, colliding, smashing into each other. Second assumption. Is this mine or someone else's? I think that's someone else's. Okay, got that? And thirdly, we don't want any attraction between the particles. So what I mean is, they would have to be neutral, electrically neutral. We don't want situations where a positive is being pulled towards a negative or anything like that. And 4, we ignore gravity. So obviously there's gravity, but for our ideal gas we ignore it, which kind of makes sense because the particles move around the room freely. It's not like they're all fall into the ground like ping pong balls. Yeah. Okay, got that? So that is balls. Small balls bouncing around in a box with no gravity, basically. That's what an ideal gas is. And here's a picture. Now, what I'm about to do with you now is a proof. The proof itself is not on the exam, except they will ask you things about the proof. So, they will not ask you to reproduce the whole proof, because it's quite a long proof. But they will test your understanding of the proof by asking you questions about part of the proof. So they might say, what in the ideal gas model or the kinetic theory model, what is the interpretation of pressure? Or something like this. They will ask you a question to make sure you understand the proof. So of course, please, you must write the proof down. And you don't need to know it off by heart, but you need to at least understand the logic in the proof. Okay? So let's start looking at the proof now. Can I have a look at it? Dear. Right. So before we start looking at a complicated problem like this, this is this box here with all the particles in it. That's a little bit difficult. Let's start by just looking at a straight line. So we have one particle here, and it goes across, it bounces off the wall, comes back, bounces off the other wall, and is back at the start. We'll just look at this first before we look at this more difficult 3D problem. We'll just look at 1D. Okay, so in the beginning, the particle has a mass m, and it heads to the right with a speed of v. And then afterwards, it's coming back with v. So the direction has changed. One more thing. We'll just say the box is L by L by L, so the distance here is L. Alright. So what is the delta P? Well, that's the momentum at the end minus the momentum at the start. The momentum at the end is minus mv, because it's heading left, minus, and the momentum at the start is mv. So that is minus 2mv. That's the momentum, the change in the momentum. Is that okay so far? Yeah. Now, let's just divide this by the t. So we get this equals this. The time taken here. Now, the reason I did that is because you know what this is. Yep.
Why is it
minus?
Yes.
Yeah, because why this is minus or this is minus?
No,
this one? Yeah. The reason is this one is the momentum at the end, and at the end it's heading left. At the beginning it's heading right. So this minus here is because it's heading left. This minus here is just part of the formula. And this is a plus because it's heading to the right. Is that okay? Yeah. Now what is this equal to? It is, yeah. What F exactly?
Minor.
Yeah, but I mean on the diagram I should say actually. What F is this on the diagram? Yeah, it's the force acting on the particle. Because the particle was heading right and now it's heading left. So there must have been a force to change its direction. There's a force here acting, it acted left. In fact, it acted at the moment it crashed with the wall. But what I really care about is not this force, but rather the reaction force here. Because the F that acts to the left, the wall would have reaction force equal to this acting to the right. Which, you know, think about it, it makes sense. If you picture the wall here and the particle comes in, it hits the wall bends a little bit, and then the particle heads back. Well, clearly we can see that there's an outward force here on the wall. So I'm going to drop the minus because I actually care about this F. So I get F equals 2mv over delta T. Alright, do I still have everybody with me? Nobody's lost? Okay so far? Yeah. Right, let's try and simplify this a bit more. We know that pressure equals force over area. Yeah. So here, that means force equals pressure by area. So I can change this into PA equals 2mv over delta T. Okay so far? Now what is the area in this picture? What's the area of the wall here? The area, yeah, is L squared. I think you're thinking of volume. You said cube, didn't you? Yeah. Oh dear. So that's PL squared equals 2mv. Now we need to do something about the delta T. If we think about this triangle, distance, speed, time, the distance that this travels is what? Well, a distance, not displacement, yeah. Yeah, you thought I was trying to trick you. Distance. What's the distance? Is it L? No, it's 2L. 2L. That's the distance. And what's the speed? The speed is v. Although it changes direction, its speed is always v. And the t, we call it delta t here. So what's the formula for delta t? It's 2L over the v. Now that's nice because I can bring the v up there, and I can bring the 2's cancel, that's nice, and I can bring the L up to the left. So now I have PL cubed equals mv squared. Now it's getting interesting. What's this L cubed? Volume. Now, I shouldn't have used the letter V, so I'll write my volume like this. Fancy fee. Equals mv squared. Okay, I will pause for a moment to make sure everybody has everything down here before continuing with the proof. You have all of this? No, not continue. What am I saying? I need to give you a chance. Did anybody upload their main body yet to Moodle? I put a link on Moodle. I would love you to do it on Moodle because then I can mark it and give you feedback on Moodle.
Can you put pictures into Moodle?
I believe so. Yes. Yes, I should be able to. I'd be shocked if you couldn't.
But I did put a picture in. I will.
No, you don't need pictures. No, don't freak out. This is only. I really care about seeing what you have to say. References and pictures and diagrams can be done in the second a look at it. You have pictures already to put in?
MS Paint.
Oh, wonderful. Nothing beats MS Paint Classic. Did you know that Microsoft wants to get rid of MS Paint a year ago? You knew that? Yeah, shocking. It's like their best feature.
Yeah.
I mean, what else is their best? Like, I mean, it's not going to be Internet Explorer. I mean, what else have they got? Solitaire, maybe. Coursework 1, main body or something like that. It's like the second link.
800, 900 words.
Yeah, I read about that. Yeah. Did you find the link, Bruce? Do you want me to show you? Yeah. Are you on the page? Yeah. I think you wanted to do it. Oh, there, coursework. Yeah, coursework 1, the main body. So if you click that, where do this here? Whoa. You can. Oh yeah, you can click attempt and then you can paste it in. Well, don't do it yet because you don't have it. But you can click this button and then put it in. Oh yeah. Yeah, well, I think I have, no, I let you do it twice. So what will happen is, you will put it in, I'll give you feedback, and then you can put it in again. Do you understand? Yeah. Ready to continue? Yeah? Okay. So now, we have a teeny problem, because our calculations was just for one dimension, but of course the particle is moving in 3 dimensions. There's actually a very easy way to deal with that. Let's go to the right. Alright, so here is our box. And the particle is moving around in 3 dimensions. And although it's moving around in 3 dimensions, we can still, like in projectiles, we can still think about it as having an x, a y, and a z part. We can look at it as components. So then the real question becomes, okay, this is moving with a speed v. What are these components? So this will be v1, we'll say, this will be a v2, and this will be a v3. And you might say, oh goodness, that's quite hard, Stephen, because there's an angle here, and there's an angle here, and you have to resolve it. There's actually a very sneaky way to deal with this. We reckon, on average, v1 should roughly equal. Now, by the way, when I say v, I mean the speed, not the velocity. So all of these numbers, I only care about the speed. So I'll just write maybe s here to remind me it's speed. So v1 should roughly, well, I'm thinking about this too much, should roughly equal v2, should roughly equal v3. Now, roughly speaking, all the components should be the same size. Now, does anybody have any idea why I can make such a claim that when this is moving around in 3 dimensions, on average, each component will be about the same? Any reason why I might be able to say this?
We can calculate that.
So what's your reason? Why can I say this? Because?
This is reasonable.
Yeah, but why is it reasonable? That's the key question. It is reasonable, but why?
We can
Yeah.
calculate
Yeah.
the exact
We can or can't?
can.
But that doesn't make this reasonable. Nice try. You have an idea?
Is it because of the length?
No, not the length.
It's an idea, yeah.
Can mount our feet?
No. Nobody knows. No ideas, no? Well, you have ideas, but... Think about the opposite. Suppose I said, on average, V3 was bigger than V1 or V2. What would happen if that was true? If on average V3 was bigger than V1 or V2? Then, yeah, there'd be a tendency for the gas to move up to the ceiling. But because the gas fills the box evenly, then we can't say any direction is preferred. In other words, there is no preferred direction, so each direction must be equally likely. So these we can all just call x. So this is an x, this is an x, and this is an x. And Pythagoras, our friend, said v squared should equal x squared plus x squared plus x squared. So x squared should equal 1/3 v squared. Or the other way around, you could say v squared equals 3 times x squared, whichever way you want to state it. So in other words, if in the beginning I started off by drawing this as v, and I want to make it 3 dimensions, then all I have to do is say there's a v here, there's a v here, and the 3-dimensional speed would be 3v. If that's a v squared and a v squared and a v squared, Pythagoras says this one would be square root 3v squared. Yeah? Yeah. Or just 3v squared if I only want the square. What the point I'm trying to make is, right now this is 1 dimension and the v is the speed. If I want to go to 3 dimension, all I have to do is simply divide by 3. That this speed gets split evenly into each component. So this is like the trick to go from 1D to 3D. Yeah? Oh, but this is just ramblings of a madman here. You want to write this down? Alright, okay.
Why we have to know V here?
Well, I don't really care about knowing the V, because when I look back here, it's the V squared that's in my formula. So I can just not bother with the square root and just care about what the V squared is. So I don't need to know the V. I just actually, the formula just has V squared in it, so I don't need a square root.
But why 3x squared? I mean, there's x squared and 3 infinite 2.
3 dimensions.
Oh.
Yeah. And that's actually important. You realize if you went from 1 dimension to 2 dimension, then the trick will be to divide by 2. Now, let me give you an example of a question they might ask in the exam. We're not finished the proof, but just to show you what they might ask. They might say, in the formula, what was the reason for the 3? So, I'm not finished the formula yet, but so far I have a 3 in it, you can see? An exam question might be, in the formula, why is there a 3? And the answer is, because it's 3 dimensions. That's where the 3 came from. Another question might be is, what is the cause of the force on the wall? And the cause of the force on the wall is the change in the momentum of the mass. The delta P in the mass is what caused the F here. If I look back here, this F here on the wall was caused by this of the particle. Yeah? Do you have this? Can I continue?
So we just add 1/3 to the formula.
Basically, the trick is to go from 1 to 3. I can just do this. Yeah. Continue? Not yet, okay. Yeah? Continue? Yeah? Okay, so, little trick now. I'm going to multiply both sides by, no, what I'll do is, I'll put a 2 here and a half here. Now, what's the reason for that? Well, what do I have here now? Kinetic energy. So the pressure times the volume is equal 2/3 the kinetic energy. Okay so far? Now, how many particles did I look at in my picture? Just one. If I have 2 particles, then everything stays the same, except this will be twice as big. If I have 3 particles, then this will be 3 times as big. Yeah? So let's say I have, this is for 1 mass. So let's say I have n masses. So all I have to do is multiply this by n, and instead of this being the kinetic energy for 1, it's actually the kinetic energy of all of them. So I'll write down here total kinetic energy. Yeah. Now, I don't really want an n in my formula because I have no idea what the n could be. It'll be a big number. So I'll divide by n. Total kinetic energy over n. Now this becomes quite interesting. What is this? The total kinetic energy divided by the number of particles. Average kinetic energy. So PV equals 2/3 kinetic energy average. Yeah? Continue? Yeah? So, let me see. Yes, actually, I just need to take a side note here. Just to go from here, or here. Yeah, here actually. So this is fine, but actually there's an interesting point I can make here. Remember we said we don't consider gravity. So what's the potential energy then if we're not considering gravity? It's actually 0. So the total energy will be the kinetic plus the potential, but the potential is 0. So actually, not only is this the total kinetic energy, but it's also the total energy. So we can say NPV equals 2/3 the total energy. So, in other words, the total energy will be 3/2 NPV. I think that's what I have here. Oh no, I have it wrong. I have an N somewhere and I shouldn't. What did I do wrong? I shouldn't have that N there, should I?
What is 3 over 2?
Oh, I just rearranged it. What the fudge? This N shouldn't be here. You shouldn't be there.
Only one person.
Yeah, I screwed up something here. Something went wrong here. Something went wrong.
The total kinetic energy.
Do you know what? Actually, I think it's here. Sorry. Yeah, apologies. I should not have the N here. The N shouldn't be here. The reason why? Well, because pressure and volume, it's for the whole box. It's not pressure and volume for one particle. It's already a total. P is already a total. It's the pressure of the box. V is already a total. It's the volume of the box. It's not like each particle has another PV. So I should never have put the N here. So that was wrong of me. Bad Stephen. So that changes this a little bit. But actually I don't care about this. Delete that and instead just go straight to here. No N anymore. And you know what the stupid thing is? I made the same mistake last time I did this. Just not learning.
Okay.
Oh, thank you. It's kind. So this is the result I wanted. Total energy is 3 over 2 PV. That's the result. Yeah, it's a good thing they don't ask you to do this proof in the exam. A bit tricky, as you can see. I assume nobody has seen this proof before, or yeah. New proof? New, yeah. Continue? No.
That V equal volume.
Yeah.
P equal
Pressure.
pressure.
Yeah.
And total energy. Total energy is just kinetic energy.
Yeah. In this model, it's just kinetic because there's no potential.
What PV equal total kinetic.
Yeah, I suppose, Bruce, really maybe I should have written T here, because this is still the total, but it's just for only one. So it's still the same if it's N. You know, because this is already a total, because it's for the whole box. Yeah.
What is potential 0 again?
It's one of our assumptions of an ideal gas law. We simply ignore gravity because the particles move freely around the room. It's not like the ping pong balls that all fall to the ground. So gravity is not important for the gas. Yeah.
Ignore
Gravity.
Ignore meaning 0.
Yeah. Yeah. Continue. Yeah. What makes this formula so interesting? Well, what makes this so interesting is it's very easy to measure the pressure. In fact, you can use your phone to measure pressure. There's an app that you can get that measures pressure in a room. So measuring pressure is simple. And what about measuring volume? Simple. I mean, just use a meter stick. You can measure volume. But what about measuring the total energy of each particle in a box? Easy or hard?
Easy.
Easy.
Hard?
Well, I've never tried it, but I would imagine trying to measure the mass and speed of every molecule in this room would be hard. Wouldn't it? Right? Don't look at me like I'm crazy. Like, you have to agree with me. Wouldn't it be difficult to measure the speed and mass of every molecule in this air?
Hard.
Yes, it would be very hard. In fact, maybe even impossible. But what's so nice about this formula is something which is very difficult to calculate can be equal to a problem which is very easy to calculate. So by simply knowing the pressure and the volume of the gas, we can know the total kinetic energy of the molecules in the gas. Quite interesting, I think.
Who makes these?
This was probably somebody like the people who studied this about 100 years ago would have been people like Kelvin, Joule, Einstein. These people studied these topics about 100 years ago. Maxwell, might have been on Boltzmann. Might have been Boltzmann. Boltzmann, yeah. I think maybe Boltzmann, yeah. No, not hundreds of years ago. Boltzmann was maybe 150 years ago. Yeah, it's not that old actually. It's quite a new, compared to thousands of years of history, it's quite a new area of physics. Yeah, continue? Yeah, okay. It may seem like we know how much work is done to a gas when we change its pressure and volume, since we have this here. However, we just need to be careful. This formula tells us how much energy is stored in the gas. It doesn't tell us how much work is done if we change the pressure or the volume. So, for example, if I have a gas, it has energy stored in it. If I want to know how much kinetic energy is stored in it, I use this formula. But if I want to know how much work is done to change the pressure or the volume, I need a different formula. Let's have a look at that one. Can I continue? Yeah? Let's calculate. So, can I scroll down? Yeah. So let's imagine I have a gas, and let's keep our life easy. Let's put the gas in a cylinder. And this gas has a pressure and it has a volume. And then I come along and I push down on the gas with a force. So I'm definitely doing work. I'm pushing down by a force. How much work do I do? Well, what will happen here will be, it'll be the force times the distance. So we'll call that distance here, we'll say it's d. Yeah. Now remember what the formula for force is. If pressure is force over area, then force is pressure by area. So this would be PAD. But what is A by D? What is this area by this distance equal to? Volume. Or rather, not the volume, but the change in the volume. The amount of volume that you lose. Change in volume. So, what letter should I use to represent that? Well, I'll write it as delta V. This is the volume that we lose. So we actually have this formula. Now, I should point out, there's a small problem with this formula. When we push down on it, we actually know what happens to the pressure. In real life, what happens to the pressure. It increases. This formula only works, we kind of need to imagine that this is constant. But of course, we all know that the P will be increasing. So, to be clear, I'll just write this. Work is roughly the pressure times the change in the volume. That is how much work is done to compress the gas. Oh dear. I guess there was more to do in this lesson than I remembered. a simple little proof compared to the last one. You know, the last proof was a daddy proof and this is a baby proof. No, the last one was a grandfather proof and this is a baby proof. Or grandmother. I'm not sexist. Yeah. Okay, continue. Yeah? You got this? Okay. So we have this formula here. Yeah? Okay, we have one more proof to do, and then we have some examples. But I think we only have 1 hour now. So rather than trying to rush through this next proof, we'll just continue this in the... What's our next class actually? Sorry, our next class is what? And is that 1 or 2 hours?
1 hour and 1 word. You have it.
So we need to continue this lesson after the break because on Friday we'll have a tutorial on whatever was problems in the mechanics and the new chapter this week, okay? So there's one more proof left and then we have some examples, but we won't get to do that until after the break. So I'll see you on Friday for physics tutorial and assessment support. Please upload your main body before Friday. I would like to give you feedback before the class. Yeah, don't email it 10 minutes before the class. I won't have time to give you feedback. At least 3 hours before the class. At least. Thank you, Bruce. See you Friday. No, actually, I might see you tomorrow at the university.